Alright, good morning everyone. Hope you're having a good Saturday so far. Today we're going to talk about image classification in C# using the open source cross-platform library ML.NET. And we're going to see how we can classify images, both using Jupyter notebooks as well as using automatic machine learning in Visual Studio. Before we get started with the examples here, I do want to give you a brief overview of CNNs and just some quick words on what ML.NET really is. So deep learning, as you may know, is a subset of machine learning, right? And we have it all around us in your Siri or your Google Home, Alexa, whatever you have around you. And it's also something we use for image classification, and it's heavily used at airports, for example, for automatic passport controls, especially in Europe, to ensure that the passport holder is actually the one that is actually there. And we can also see that it's used by the police force, as well as authoritarian regimes to control their citizens. But in general, I would say that image classification and the powers of computer vision is used for good purposes around the world, and I hope that will stay like that going forward as well. But in this stream, we're not going to talk so much about all the things it can do, but we're going to talk about how it works and how we can create our own image classifier using C#. So to do that, let's first take a look at what a deep neural network is and what a CNN is. So let's see if we can start this one here. Okay, good. Well, that's fine. My computer is dying. Apologies for that. All right. So let's first look at what a CNN is here. So a CNN consists of a normal fully connected layer here on the far right, which means that we have neurons that are connected together with the preceding ones as well as the ones afterwards. It's fully connected. For those who are not too familiar with neural networks so far, it's just a linear abstraction of algebra. Each neuron has its own computation, more or less multiplying inputs, adding them up, and then normalizing it for output, which allows the network to handle multiple permutations here. We have an output layer right here to the right, which is going to define which class we are seeing. For example, car, truck, van, or so forth. It's going to both supply the class, but also the probability of that being in that class. For example, we'll say that, yep, it's 60% certain it's a car, but that probability is going to be higher than anything else, so that's what we're going to go with. In the middle here, we also have a different kind of layer. We have something called a convolutional layer instead. So why do we have that layer, not just a fully connected neural network? Well, to understand that, we need to understand how we are massaging and handling the image input. As this representation is trying to show, we have 3 different color channels in each picture for anything that's color, right? And each color channel also has a grid of pixels. So for example, we can have a 1980 times 1280 size picture, right? So we have thousands and thousands of pixels. And each pixel has a value, which means that it is a feature that's going to feed into this network here. But not to overwhelm the network, to make it too slow and imprecise, we only want to take features and pixels that are important and actually tell us something. To do so, we have this convolutional layer and pooling layers here, which more or less pass over a filter over the image to get the important features of the image. For example, it may find that these areas around the wheel are important or these lights are important. And it will then downsample the image here, going further down and down to ensure that only the most important features of the image is then fed into the fully connected network so that we can get a good prediction coming out. So just think of this layer as a way of downsampling the image, and then we do regular neural networks on the right side here to get a prediction on the right. All right. So what is ML.NET? Because we're going to use ML.NET here to make our predictions. So what is ML.NET? Well, ML.NET is an open source library for .NET developers to do machine learning in. It's more or less like scikit-learn for Python, but it's more for C# developers. You can deploy a model as an Azure function, as part of your ASP.NET Core application or a desktop application. It's really your pick, which is one of the powers with this library. You can do a bit what you want. It also supports automatic machine learning and has Jupyter Notebook support, which means that we can run our models and train our models in a Jupyter Notebook, just like you do in the Python world sometimes. One of the cool things is that it supports transfer learning, and that's what we're going to leverage today. So what is transfer learning? Well, transfer learning is a way of taking a pre-existing machine learning model, for example for computer vision, and then just retraining it on a specific task. Google and Microsoft and all these big companies, they have already created good deep neural networks for computer vision to detect what a thing is. But it of course doesn't know everything. It may not detect your company logo, it may not know how to detect your dog or cat specifically, right? So what we can do then is we can take that existing network and we can just feed it in a couple more images to ensure that it now knows these specific items too. I usually see it as a human knowing how to detect people around you, but it may not know exactly who that person is or if it's your friend or not. But if you tell me that that's your friend and that's Jonathan or Joe, then I will remember that going forward. And it's the same kind of concept with transfer learning. So how can we do this in a real scenario? Well, we're going to start off by building an image classifier for product groups, and we're going to do it using ML.NET with Jupyter. And if you're interested in doing that yourself, you can go into my GitHub repo here, and you can look at those examples yourself. And the address here is in the top left corner. It's github.com/a/ml.net-jupyter. So to do this, we need to kick off a Jupyter Notebook locally. And to do that, what you can do is, actually let me show you. You can download Anaconda. So Anaconda is a distribution that comes with Jupyter Notebooks. And that's the easiest way to get all the plumbing and everything up and running. So just download the Anaconda distribution and install it, and you'll be off and running. Once you have that distribution installed, what you can do then is to go to the folder where you have your notebooks, or where you want to create your notebooks. And in my case, it's going to be ML.NET Jupyter and source data view, I think. And then you just type Jupyter Notebook, and it's going to serve a web page for you with your notebook, just like this. Perfect. And what we can do then is, in our case, we can go into our repo and we can open our notebook that we are going to leverage. So this can take a little while, so I'm going to kick this off real quick while we discuss what we're going to do here. All right. So what are we going to do? Well, we are going to go in and look at that. And just one moment here, I'm going to open up the images. So what we're going to do is we're going to take all these images here, and we are going to determine what product group they belong to. You see bags here, you see rucksacks, you see people, you see shirts, and you see everything like this. So think of it as an e-commerce site, right? And you want to figure out what all these things are without having a human intervention in that space. So what we're going to do is we're going to feed all these images to a deep neural network with the labels of what product group they are in, and we're going to train the network to determine that that's a shirt and that's a rucksack. And then we're going to feed the network some images that it hasn't seen yet, and we're going to see if it's able to predict those images correctly. So, sounds good so far? Awesome. So, what we're going to do now is we're going to go back to our ML.NET Jupyter Notebook, and we're going to try to understand what we're doing here. So, each Jupyter Notebook has cells. They're either a markdown cell, like this, where you can have text and explanations, or there are a cell like this, which is code, right? It's type code here. In our case, we're running a C# kernel that you have to install, and the instructions are in the repo. But it allows us to execute C# in these cells. And the cool things here is that we can execute part of the C# code here and not the rest. So we can, for example, load our images into memory in one cell, but not do anything on those images until we execute the next cell. So what do we need to do first? Well, first of all, we need to install the ML.NET library, which is the machine learning library we're going to use today to do image classification on. That's just installed as a set of NuGet packages, And in a Jupyter notebook, the way we do that and our dependencies is hash r and then define where we're going to find the packages, so NuGet, the name of it, as well as the version. So we need a standard package, which is this one here, plus we need 2 additional packages just specifically for image analysis. And as we're actually using TensorFlow in the background here, we need a TensorFlow distribution. So ML.NET is very powerful, but it does not want to try to recreate TensorFlow. It does not want to be a deep learning network by itself. It's just going to leverage TensorFlow under the surface. And you can think of this like Keras, for example, in Python, in the Python world. Keras by itself is not necessarily a deep learning network, but it's an API on top of TensorFlow that makes it easier to handle. So it's kind of the same thing with ML.NET. So if you execute SL, we're going to see that we're installing packages, which is awesome. What we then do here is creating 2 classes to represent our data. And I don't want to dive too much into this, but the article class right here represents a row in a CSV file that defines what the image ID is and what the product group is. So we can link an image to a product, because we need to tell the network what a certain image represents when it's training it. And that's what we're doing with this article row right here. We then represent a class for the image data. So we can tell, we can kind of hold a list of images with a path to the image as well as the product group here, which is going to be very useful further down. What we then do here is, and I will zoom into this part here, is that we are defining 2 paths here. One for the images and one for the CSV file containing kind of the metadata that we're going to use. So again, each row is going to define the ID of the image as well as what product group it is. We're then going to use the CSV helper NuGet package, and we're going to read all the rows in the CSV file, and we are going to combine and create an enumerable of image data, which is the path to the image as well as a label. And it's pretty cool here because we can create a function in one cell and we can execute it in the cell below like this. So I think that's just fantastic. I really love this. This is a really cool thing. Alright, so this is just regular C#. There's nothing to do with machine learning so far. We're just trying to get the images into memory so we can handle them. And that's what we've done right now. We have the images in an array here, or in a list. We're now going to transition in a little bit more to the machine learning world and see what we can do here. What we're going to do here is we're going to create an ML context, and this is an ML.NET construct. And the ML context is somewhat, what can you say? It's somewhat like a DB context and entity framework, just that is for machine learning specifically. The ML context contains all the transformations and the methods and everything else we need to successfully create a model and to evaluate it. In our case here, we can use the data catalog and load from enumerable to load our images above here to a data view. And the data view is just a representation of the data such that we can handle it and work with it in memory. Once we have the data view here, we can then use a method called shuffle rows here to shuffle rows around a bit so it's random. Because, for example, maybe we have the images in a certain order and we don't necessarily want that because we want them to be completely random, so we don't have a model that is skewed one way or another. Perfect. And if I zoom out here, I don't want to be too close in here. The next step here is a step we're going to do just to read the images into memory. Right now we only have a path to the image and the label, but we don't actually have the bytes and the pixels of the image. So we can use a transformation here in the transformation catalog, and we can map our label, which is the answer we're predicting, right? That's going to be product group. We can map it to a key. Because we don't necessarily, in machine learning we can't handle strings very well, so we need to have the strings represented as a key of some sort. And that's what we're doing with this method here called map value to key. What we then do is we're appending a transformation here for loading the raw images to bytes. And we're saying that, hey, the input column you're going to use here is image path. That's where you're going to find the image. And the folder where you're going to find the images are here. And please upload those to a property called image. And that's going to be of type byte array. This is, of course, in the background. You don't need to worry about it too much. All you need to worry about using this information when you load them into memory. And then we do 2 things here that is not so important to think of right now. I just want you to focus on this step as, hey, we are going to load images into a byte array, and we're going to have each byte array mapped to a product group of type key. All right. This is pretty much boilerplate code right here. So before we start training our model, we can take a look at the distribution of our data and see if we have an uneven data set in some ways, right? So if you take the labels, and again that's the product groups of the shuffled data set here, we can then use plot a histogram using the XPlot library to get the number of images in each category. And we'll see here that we have 39 ties, 132 belts, and 521 shirts, and so forth here. So we have a lot of shirts, which is a little bit unfortunate because most likely the model will be a bit skewed. But that's just alright right now. Because in general, what you want here is an even distribution of categories. The more even it is, the better it is going to be at detecting certain things. For example, it's going to be very hard for it to detect blazers because it's only seen one blazer in its life. But for our purposes here, this is going to be a good example to show. Alright, so once we have our shuffled data set here, what we need to do then is split it into a training and a test set. So why do we do that? Well, we do that because we want to train our model on a set of data that it hasn't seen before and make sure we fit the network to that set of data. But then we want to keep and hold out a set of test data that we can use to evaluate the model's accuracy. It's in deep learning especially, there is a chance that we can overfit our model to make it know the training data too well, but it's going to be poor at predicting new data. So when having a test set on the side here, we can ensure that our model is agnostic and can actually find a shirt in the wild as well, which is going to be important. So we do the split here, and it's method for it automatically. By default, it's going to take 90% of the data as train data and the rest as test data, but you can overload this method easily and provide your own split if you like. So now we come to the machine learning part here that is important. What we're going to do here is we're going to use the multi-classification catalog here. In that catalog, we're going to go into trainers, which is more or less just algorithms, and we're going to say, hey, we're going to do image classification here, and we are going to output a predicted label, more or less, that we're going to get. So please tell us what we are seeing in an image. And to this image classification, we're going to pass in some options. So what kind of options do we have? So there are a couple of things that are very straightforward, like the image, for example. The feature we're trying to use for predictions is an image, and in our case, it's going to be the image byte array. And what we're trying to, the answer that we know is the label as key. And so think of this as the product group. So this could be a shirt, this image could be a shirt, and this label could be shirt. That's as simple. Or we can have an image here, byte array of a sock, and the label as key can be a representation of a sock. Okay. We then have some more machine learning or deep learning specific options here that are important. The first one here is architecture. So ARC stands for architecture. That means which kind of network are we going to use for our transfer learning task. The ResNet one is a Microsoft network. We can also use an Inception v3, which is a Google network, and there are also a couple of other networks we can use. When we define this, the library is going to download that network locally and unfreeze some of the layers and retrain them for us. Epoch here is just how many times are we going to try to go through the network and train it. So that's kind of a number of training rounds in some ways. And batch size is how many pictures should we send for each time we go through the network. So it's 10, for example. And so in general, we will go through, but in one epoch, we will go through whatever the number of pictures divided by 10, more or less. And then we have an epoch, and that's complete. And then we go through network again. So each time we go through a network, what's going to happen is that the network is going to adjust its internal values, in this case weights and biases, to be closer and closer to the truth. So each time we go through a batch size, it's going to calculate how far away from the actual value was I. If I predicted a shirt and I said it was a sock, how far away from the true value was I? and then it will adjust its weights and biases to make sure it's closer and closer to the truth. We're also then going to pass in a validation set here, which is useful because that's going to give us an accuracy measurement as well going out. So when we call the fit method here, that's when the magic happens. That's when we're passing the training set to the model or the training pipeline, and it's going to output a trained model. What MLNet is going to do is going to output the TensorFlow outputs when it's training the model here. The first part here is just loading the images into memory. This is pretty boring. But if you go down here, see, we start doing the training. So each of these is an epoch here. You see epoch 0, 1, 2, 3, 4, and it's 5 total. And we will see here that the accuracy of the first epoch is 0.98, so 98%. And then the next epoch is 99.8% and so forth, and we'll see it's getting better and better. So it's pretty quick at having a good model. And then the fifth epoch, we are already at 99.9 more or less % accuracy, which is awesome. And it will then say it throws 2 variables, which means that it had more or less retrained two variables in this existing network to for our purposes. What we then do is that we are taking the test set and we are transforming that to predictions, and we're trying to get some metrics here. Because once we have a deep neural network, we also want to get the evaluation metrics of it using the test data completely. And this will tell us more specifically if our network is something we want to keep or something we want to throw away. So by getting our predictions here, we'll get an answer or a class to predict plus probability, and we can use that to get our metrics. This will, for example, show that we have 99% accuracy. It will show something called area under the curve. It will show maybe recall and precision to make sure that we don't have a skewed model that favors class over the other, and so forth, which is going to be useful to see. I personally prefer a heat map instead, because a heat map to me is going to give me a better indication of how the model is confusing different classes. So we can use a library called XPlot here to create a heat map. And a heat map looks like this. A confusion matrix looks like this, and it's based on a heat map. What we're seeing here is we are seeing predicted values on one axis and the true values on another axis. And if we have a perfect model, we will only see values here on diagonal. All right, that's the only thing to see here. We can see that we're pretty good to the truth here. We mostly have values here, but we do have value here for socks and jeans. That means that one of the test images that we used, we confused socks with jeans, which is interesting. I would assume that socks and jeans are very different, but apparently a machine learning model don't see that difference. It's not terrible, it's a pretty good model still, but the confusion metrics here could tell us that, yep, we need to maybe augment the images of socks and jeans and maybe have some more different colors, shapes, and sizes to make sure the model can really distinguish between them and not confuse them in the future. But yep, this is not necessarily a way to give metrics, but it's a great way to understand how a model thinks. Once we're done with that, we can save the model as a zip file, and we can then use it in our application, for example, an ASP.NET Core application or Azure function, or what have you. All the models are just saved as a zip file, and it's pretty straightforward, and there's no magic around that. Cool. All right. So that was using MLNet to create an image classifier in Jupyter Notebooks. But what if you can do it in Visual Studio as well? Of course you can, and you can actually do it much more simpler. So if we open up Visual Studio, we can try to use automatic machine learning for this purpose. To do so, we can create a new project, and we can create a .NET Core console application here. And let's call it image classification, Twitch. Create next, which hopefully will get Visual Studio to open up and do something useful here. Okay, so we see Visual Studio opening up here, which is great. Perfect. Alright, so what we're going to do right now is that we are going to use automatic machine learning to train a model on a set of images. Instead of doing product groups, we are going to train a model to detect flowers here. So we have different catalogs and we have images of flowers, so daisies, we have dandelions, we have roses and so forth. And we want to create a model that can distinguish between these different classes. To do so, all we need to do is right-click on the solution, or in product, sorry. Click Add, and then Machine Learning. This will open up the model builder. And to get this option, what you need to do is go to extensions up here and manage extensions and download the model builder. It's a free extension, it's easy to use. You can also install it from the web. But the model builder allows you to pick a scenario, for example, binary classification, issue classification, price prediction and forecasting, and so forth. And as of November, you can also do image classification here. If you click at image classification, it will tell us to please select a folder where you have each type of image in a separate folder. So again, labels here. It's going to be roses, it's going to be sunflowers, and so forth. For our product group scenario, for this to work, we would have to put shirts in one folder and jeans in another folder. But right now, we already have the structure set up for our images. So we'll go straight there and press OK. And what it'll do here is load those images into memory, and it will show a preview of all the images. And we can see here on the count that we have a nice distribution of images, which is ideal to get a good model. So once we have selected our data, we can go to the training step, and we can just hit start training here. And it's going to tell us here that it's going to use ResNet 50 network under the surface, and it's probably going to train it until it finds a good model. So I know there's a lot of good work being done on this specific task right now in the MLNet team, and I know that they are currently working on supplying support for this in Azure Machine Learning. So instead of having all this training being done locally, which you can see here, you can actually provision this computation in a cluster in Azure Machine Learning, which is going to be very useful for real-time scenarios where the images are not this small and the images are not this few. Because it takes a lot of power to do this training, and you in general need a GPU of some sort to be efficient here. But if we wait here a bit, we'll see that we probably have about 50 or 60 more images remaining before we can start training this. So what it's doing right now is just loading the images locally. That's all it's doing. And we should be almost done here. And now it's going to load the test images, I think. Or it may start training. The best part of streaming is that your computer is both occupied with streaming, which takes a lot of power, as well as training a network. Alright, so here we see we are running our epochs just as we did in the Jupyter notebook here. We are running the first epoch. Let's see, it's doing a lot of things here. We can see here that we run the first epoch, so we run 24 epochs in total, and we had a learning rate of this. And we can see here, the really cool thing here is that we have a variable learning rate here, which is something you can also define. So in the beginning, it kind of swung back and forth a lot, but eventually it was getting smaller and smaller to try to find this optimal model. And it started off with like 90% accuracy, and it ended up with 100% accuracy of the test data. So we have a really solid and good model here, which is pretty impressive. And I believe after it's done that, it is now complete with the training, and it's most likely saving the model and getting some metrics based on the test images. Interesting. Or it's training it again, honestly. This is I haven't tried this functionality actually since the new release, so this is to be new as well, which is very fun. We'll wait for this to complete and see what we get, which is fun. So again, loading the images. All right. And here we go. It's training the model again, and using similar learning rates. And I'm curious if it's decided to train using a different network here or not, and that's the reason why. Okay, let's see if it completes here, or if it's going to do this again. Let's see. So as you can see, it's useful to do this somewhere else, because it's takes a lot of power to do this, and it's not so good for your computer always, especially if you don't have a more of a desktop computer instead that has a bit more power than I. Alright, so it's doing it again. I'm going to let it do that. I think what it's doing is training with different hyperparameters and different networks. In our case, we don't need that, so I'm just going to cancel training right here. But eventually what it will do is going to finish up, and it will give you the metrics, and it will evaluate it based on test images, and you will then be able to get the code. So not only will you be able to get a model here that you can use for your own purposes, but you're also going to be given the code that is used to train a successful model on. And this is fantastic, because what it will allow you to do is modify the code slightly if you have more domain knowledge that will be useful in your scenario. So I highly recommend you check out the model builder, both for image specification, but also for other machine learning tasks, and see what you can do. Alright, with that, I thank you very much for joining this stream today. I hope you learned something. If you have any questions or just want to chat about machine learning in C#, feel free to reach out to me on Twitter or LinkedIn, and I'm happy to answer those. Have a great rest of your weekend, and talk to you next time.